There are some materials which have always been seen as valuable, some a little bit too valuable for me. But for centuries, people have made use of materials like diamonds and gold. Sometimes, as in this cathedral, because they're rare and treasured. But at other times, it's because of what they're capable of, what they can do, their properties. In this programme, we're going to find out what this has to do with this, what this has to do with this, and what this has to do with this. The key to the puzzle is the science of materials. And the locksmith? That's a person called the materials scientist. Almost everything around us is influenced by the use and choice of materials. So it's important to know about the properties of different materials. If we want to know which materials are best, we need to know all about them. And that's where the materials scientist comes in. Professor Colin Humphreys is in charge of the University of Cambridge Materials Science Department. Colin, what does a materials scientist do?
Well, a materials scientist tries to understand the properties of materials, like how strong they are or how good electrical conductors they are, in terms of where the atoms are and in terms of the forces between atoms.
Yes.
If you can understand where the atoms are, their chemistry and the bonding between the atoms, the forces between the atoms, then we really know what the material will be like. It all follows from that.
People have understood some of the properties of materials for a long time. The Egyptians, for instance, knew that gold doesn't react with air and corrode, like some other metals. It's a property called being inert. Inert means that gold doesn't react easily with other materials, and that includes the chemicals in our bodies. So they used it for filling and replacing teeth. And 3,000 years later, dentists are still making use of this property. In fact, almost 60 tons of gold a year goes into our mouths. The fact that gold is inert is another reason why we see it in temples and churches like this. Because it doesn't decay, it lasts for hundreds, if not thousands of years. And not only does that make it valuable, but it means it survives the centuries for us to see today. These religious buildings also provide us with another clue to a property of gold that's been known about and put to good use. In hot countries, temple roofs were often covered in gold, not only because it was an expensive tribute to the gods, but also because it reflected the sunlight, and so the heat, keeping it nice and cool inside. This property has been used by materials scientists to help them with some very advanced technology, particularly in an area where strong sunlight can be a problem, such as in space.
Well, gold is a particularly reflective element in that sunlight, when it impacts on gold, tends to reflect it at a fairly high rate. We can expect sun to reflect at 95, 98%. I think often you have a situation where you don't want your spacecraft to get too hot. So we'll put a gold surface on the outside to reflect the sunlight and to keep the spacecraft from getting any hotter than we'd like it to be. In other applications, such as the astronauts' visors, we may find gold laced inside of the goggles so that the sun reflects from the goggles and the astronauts can see without being blinded by the sunlight.
You got it.
Extremely thin coatings of gold can also be used to reflect heat from the windows of modern office buildings. Applications such as this glass means that scientists are working with gold at the level of 1 atom of thickness. For this, you need very pure gold. I learnt a thing or two about gold and about its properties by visiting a refinery. Here, gold is taken through several stages of purification to be transformed from gold ore to pure gold bars. So what is 1 atom of thickness? Well, this gold leaf here might look pretty thin. You can almost see through it, but it's actually 250 atoms thick. We need to look a little closer. Magnified by an electron microscope, these are individual atoms of gold. To help understand these images, scientists use models to represent the relationships between the atoms, the actual structure of the material. But what can they tell us about the properties? Now, I've got a battery here connected to a light bulb. If I close a circuit with this gold bar, if gold conducts electricity, then the bulb should light up. Yeah. By being able to look at gold at an atomic level, we can see that it should be a very good conductor of electricity. Moving around between all atoms are electrons, and there are very many of these freely roaming from atom to atom. When you apply a voltage from a battery, this random movement becomes a general drift, and that's an electrical current. But for the users and designers, it's more than just one property of material that's of interest. It's a whole range of properties. So for gold, well, gold is ductile, so it's easy to work with. It doesn't corrode, so it lasts a long time. We can work with it at minuscule levels, and it's a good conductor of electricity. It's this combination of properties that means we use gold in almost every electrical appliance. Gold is at the very heart of the electronic age. Since we know that materials are composed of atoms, we can start to understand more about how materials work. Here at the engineering department at Cambridge University, they developed a microscope that can probe materials at the atomic level. Silke Althoff uses this microscope in her research. Silke, what does this microscope show you?
What it actually does, it shows me how atoms are arranged on a surface.
And how does it do that?
I show you my microscope over here. I can open this up. I've got a tiny little needle down there that I move across the surface like a record player needle, and light coming down to the end of this needle gets reflected while I sort of move over atoms. This deflection of the light beam then shows me where atoms are sit and how they are located on the surface.
This is the surface of diamond. Magnified 100 million times, we can see the individual carbon atoms that make up its very structure. Again, looking at a model of these atoms can help us to understand something of the properties of this material. With diamond, we see that the electrons are tightly bound between the atoms. These bonds are all extremely tough and are very difficult to break because the atoms are being held so firmly together. That's why diamonds are so hard. We can make good use of this. For instance, by embedding diamonds into the blade of a saw, you can get a tool which can cut through almost anything, even granite. Diamonds are at the heart of many industrial cutting processes. They're vital. As a diamond expert, Ian Clark knows a lot about the properties of this material.
Well, diamond has a number of interesting properties, but the most useful from an industrial point of view is its extreme hardness. Diamond is in fact the hardest material known to man. And by far the most important area for diamond is in the sawing and drilling of stone and concrete. As far as thermal properties are concerned, diamond is the best thermal conductor known to man. And I have an experiment here to illustrate that. If I take a piece of ice, place it in this holder, here I have two rods, one with pure copper on the end, the other one with diamond. Now diamond is something like 6 times better at conducting heat than copper, and by virtue of this it will melt its way through the ice more quickly than the copper. As far as electrical properties are concerned, diamond is an electrical insulator. It does not conduct electricity. Here we have a simple circuit which illustrates this, a battery and a bulb. If I complete the circuit, the bulb lights. If I try to complete the circuit with diamond, the bulb does not light because the diamond does not conduct electricity.
Unlike gold and other metals, diamond doesn't have many freely roaming electrons to carry the current, so it doesn't allow electricity to flow. It's called an insulator. Here, the same carbon atoms are now arranged in layers. Not all the bonds between the atoms are strong. Those between the layers are in fact very weak, so some of the electrons are freely moving around. This almost looks like a different material. It is. This is graphite. And of course there's graphite in your pencils as well. Now the movement of electrons means that graphite is a conductor of electricity. As we show this with my friendly battery, if we connect the pencil through the light bulb to the battery, the light bulb lights up. But the layers of atoms in graphite are not held together very strongly. And it's the fact that these layers can slide over one another easily. It means that graphite's a good lubricant. Sounds weird, doesn't it? But look at this. Have you ever had a new key cut? It's often difficult to get into the lock, isn't it? But if I were to coat this key with graphite from the pencil, rub the pencil over the key there, the lubricating properties of the graphite, with a bit of luck, should help me out. Easy. We've now seen that carbon atoms can arrange themselves in two different ways, making two materials with totally different properties. So, scientists' understanding of materials is now very advanced. But even so, it's been only in the last few years that scientists have discovered yet another way that carbon atoms can arrange themselves. Footballs of carbon. This is Buckminster fullerene, buckyballs. It looks a bit like soot. Any guesses of its properties? Well, it's not a bad lubricant. It's a molecule. There are no loose bonds. It's in a stable situation. But what can we use it for? Well, we haven't known about it for very long, so scientists are still looking for an application. It's a material for the future.
Bring it on!
Today, we look for a great deal from materials. The choice of materials has enabled designers to make all sorts of amazing products. But sometimes even this choice isn't enough. Now scientists are able to make new artificial materials, but they can still have traditional uses. So today, it's not enough just to be shapers of materials that we find lying around. Nowadays, we have to be mixers. Creators of completely new materials. Hi, Colin.
Hello, Helen.
Lovely. Thanks. Thank you. It's not only been in recent times that we've been mixing materials, is it?
Well, that's right. I mean, way back in ancient times, people used to make bricks out of mud and bake them in the sun, and they'd eventually crumble away. And then someone learned to add straw to these bricks, and they lasted a lot longer. That was the first composite building material.
So why are these composite materials so important?
Well, with composites, we can combine the best properties of a number of different component materials. For example, this is a piece of steel, which is very strong, but very heavy. This is a piece of plastic, which is very light, but it's very bendy. And this is graphite, pure graphite, which is very light, but it shatters.
What's all this got to do with boats?
Well, with a boat, we need something which is light and strong and doesn't fracture.
And it's a composite which has allowed the Cambridge Women's Rowing 8 to have one of the most advanced rowing boats in the country. Even the oars are composite. Their boat is light and strong. But just how strong are these mixtures of materials? Composites can be very strong. In fact, this strip can support a load of 10 tons. That's about 10 cars. And this is the machine that's going to test it. Not even a mark. So, what is this composite? We've seen carbon as diamond in cutting tools, as graphite in pencils, and there's carbon in this jumper as well, but it's not pure yet. Acrylic fibres that make up some sweaters are carbon-based, but they're not a composite. People here at the Defence Research Agency were the first in the world to make acrylic fibres into something rather interesting. Professor Paul Curtis is one of the scientists here. Paul, what's this got to do with this?
Well, here at Farnborough, we developed a technique for converting the acrylic fibres in a jumper such as this into an aircraft component such as this. The process involves the production of carbon fibres like these.
How are carbon fibres made?
Well, carbon fibres are made from acrylic fibres. In their pure form, they look like this. And we have invented a process to cook these fibres into carbon, pure carbon fibres such as these.
Acrylic fibres are heated in an oven at very high temperatures because they contain other elements as well as carbon. Passing through the oven several times, you can see the fibres changing colour as everything except the carbon is burnt off. So from white acrylic, this simple process enables material scientists to produce very pure black carbon fibres. So what properties does this new material have?
Carbon fibres are very strong, but as you see in this form, they really aren't a structural material. And we have to combine them with a resin such as this to produce a composite where we can take advantage of the properties of both materials, the strength and stiffness of the carbon fibres, the durability of the resin such as this.
But resin's not very strong, is it?
Indeed it's not. In fact, I have a sheet of cured resin here, and if I hit this with a hammer, you'll see that it is in fact very brittle indeed.
Woo!
And it shatters into many pieces. Indeed, it behaves like a glassy material.
How do you make them into jet aircraft then?
But to convert this resin and the carbon fibres into an aircraft component, we have to mix them together in a tray. And if I show you the sort of thing I have in mind, this is actually some woven carbon fibre, as you can see. And we would take this, combine it with the resin, then we stack these layers together in an oven which works at high temperature and high pressure, squashes the fibres and the resins together and produces a solid, durable component which we can then use on an aircraft.
If we look at the atoms of carbon fibre, we can see that they have the same structure as in graphite. But in a fibre, they've twisted into a spiral shape like a rope to make it stronger. Many thousands of these are then bundled together. When resin is added, it joins and reinforces the fibres into one tremendously strong material. And because it's light as well, it has lots of uses. In sport, for example. Well, the shaft of this golf club is made of carbon fibre, rather than the traditional wood or steel, and the weight saving can be put into the head. And that means you can hit the ball further. Shall we have another go? And not just further, carbon fibre can help you go faster too. This moulded piece of carbon fibre will soon be hurtling along at over 200 miles an hour as one of the most exciting applications of a composite. Materials scientists at this company are using the properties of composites, and especially carbon fibre, to help them with the design and performance of a very particular kind of vehicle. And it's not one of these. This is the body shell, now fully painted, of one of the most successful Formula One racing teams in the world. In racing, it's vital to keep down the weight of the car to a minimum. This one's 6 times lighter than it would be if it were made out of steel, which most cars are made of. Because of the way carbon fibre composites are made, combining the carbon fibres with the resin, they can be moulded into these beautiful streamlined shapes, which also helps them to go faster. But speed isn't the only thing that racing car designers need to think about. Even more important is safety.
It's on! Berger looks as though he's hanging fire a bit. And there's straight into the wall. The race will be stopped. Oh, look at that. The car's all over the place. And that is Mika Häkkinen.
Behind John Watson, who loses it. That's John Watson. And a very nasty one indeed. Torn the whole of the back off the car.
In a crash, it looks like the car disintegrates. But in actual fact, the driver is very safe, thanks to carbon fibre. This is where the composite comes into its own. It's light, you can mould it, so it's perfect for the body of a racing car. But what's important for safety is that it's extremely strong. This middle section of the car is actually a protective cage. The heart of the car is carbon fibre. And that's true of this car too. Because carbon fibre is very expensive to make, it's only used in special circumstances. And this McLaren F1 is a very special car. It's the fastest road car in the world. If you want to buy one, you better start saving now. This costs a little over £500,000. So now our understanding of properties helps us to select the uses that materials have. Our use of microscopes, knowledge of atoms, has helped us to understand why those properties exist. And we've seen how materials scientists can take materials with different properties, mix them together, and literally make new materials, like carbon fibre. I wonder if, in a few hundred years' time, it will be these new materials that we want to keep and treasure.